what happens when I take my two um, complex numbers and I divide them? Okay. R1 cosine theta sub 1 plus I sine theta sub 1 divided by R2 cosine theta sub 2 plus I sine theta sub 2. The derivation of the formula turns out to be very similar to the multiplication. There's just the familiar trick of multiplying by the conjugate. If you want to work that out, it's kind of a fun little exercise, but I'll leave that to you on this maybe snowy day to occupy you. But we are just going to go ahead and use the formula here for the sake of time. And you see here, if I'm dividing two complex numbers, I can just divide the two moduli and subtract the two arguments. So it's very similar to the multiplication formula. So this will end up being R1 divided by R2. I mean, you can see that here. But this, it turns out after you multiply by the conjugate and then use some of the identities, it turns out to be cosine of theta sub 1 minus theta sub 2 plus I sine theta sub 1 minus theta sub 2. Okay, so let's take a look at the problem they've given us. Another basically straightforward application of this formula. So Z1 over Z2 is going to be 24 over 8 times cosine of theta 1 minus theta 2. So that's 300 minus 75, 225, plus I sine 225. And then we'll give me a little more room here. This is 3 times cosine 225 plus I sine 225. That's the quotient in trigonometric form. If we want to write it in standard form, we can just evaluate these. Cosine of 225 is negative root 2 over 2. Sine of 225 is the same thing, negative root 2 over 2. So if we were to distribute our 3, we've got negative 3 root 2 over 2 plus, and usually whenever we're writing it in standard form, the I we're going to put on the far right. So we'll do this as, we can actually write this as, instead of plus and negative, we can write that as just minus 3 root 2 over 2 I. So there's our quotient in both trigonometric form and in standard form. Okay, the last topic we're going to look at is this de Moivre's theorem, which deals with powers of a complex number. So basically what happens when you multiply it by itself, and we're going to, any number of times, we're going to look at what happens when you just multiply z by z, so z squared. And there's a couple of ways to look at this, but it's probably easiest to use our product formula, right? So this would be r times r, the two moduli multiplied together, and then cosine of theta plus theta plus I times sine theta plus theta. This is just me applying the product formula for complex numbers, but when the numbers are the same. R times r is r squared. This becomes cosine 2 theta plus I sine 2 theta. And since it's a snowy day, you could multiply this by another z, and if you did, you would find that z cubed is r cubed cosine 3 theta plus I sine 3 theta, and so on. De Moivre's theorem basically is the general case. Z to the nth power, it's easy to see the pattern. R to the nth times cosine of n theta plus I times sine of n theta. So there you go. That's the final theorem we're looking at. And we're going to use that to do these two examples. Okay, so the first example with de Moivre's theorem is 1 plus I to the 6th power. And this is where you see the utility of writing these complex numbers in trigonometric form, because if we were to just raise this to the 6th power, we would have to expand this and FOIL a bunch of times, or expand it like a binomial, which there are sort of easy ways to do that, but it will actually be easier on us to write it as a trigonometric form, because that formula is so easy that we just looked at, the de Moivre's theorem. So the first thing to do here is to look at this as z to the 6th, some complex number z raised to the 6th power. And by the way, it wouldn't hurt to just get a picture in your mind of what this complex number looks like. Over 1 on the real, up 1 on the imaginary, right there. Okay. So to write z equals 1 plus 1I in trigonometric form, we need to find our modulus and our argument. So if that's our a, that's our b, our modulus is square root of 1 squared plus 1 squared. By that formula that we looked at in the first part of 6.5, this is square root of 2. And the argument is given by tangent of theta is b over a, so 1 over 1, or inverse tangent of 1 equals r theta. And 45 degrees turns out to be the one that we're looking for, or pi over 4 if you're doing it in radians. Let's write it in radians, actually. Okay, so if we're going to write our z in trigonometric form, we would write that as root 2 times cosine of pi over 4 plus I sine pi over 4. Okay, now if we want to, let me scroll down just a little bit. If we want to raise that to the 6th power, so if we want to raise that to the 6th power, we just follow de Moivre's theorem, which is the modulus raised to the 6th power, cosine n theta plus I sine n theta. So that would be root 2 to the 6th power cosine times, parentheses, cosine of 6 times pi over 4 plus I times sine of 6 times pi over 4. Excuse me. And of course, we want to clean this up just a little bit. Square root of 2 to the 6th would be 2 to the 1/2 to the 6th power. So that's actually 2 cubed, or 8. 6 times pi over 4 is 6 pi over 4, or 3 pi over 2. So write this as cosine of 3 pi over 2 plus I sine 3 pi over 2. That's z to the 6th in trigonometric form. Since they originally wrote z in standard form, we might as well write it in standard form. So let's evaluate this. Cosine 3 pi over 2 is 0. Sine of 3 pi over 2 is -1. So that ends up being 8 times 0 minus I is -8I.